Hi guys, welcome back to Nunley Math. I'm Aaron Nunley. Thank you for joining me here today for the first lesson in our new series of videos or lessons on the linear function. Now, if you've been following along with us throughout the year, you know that we have already spent a significant amount of time, probably in the 4 to 6 weeks range in my class, discussing functions in general, the different types of functions, how functions work, the domains and the ranges and those sorts of things. We now want to direct our attention more specifically to the linear function, There are actually three types of functions that most students in an Algebra 1 class are likely to encounter: the linear function, the exponential function, and the quadratic function. So we pay a great deal of attention to those three. So in this lesson, we're going to talk about linear, and in some upcoming lessons or subsequent lessons, we will spend a significant amount of time talking about the other three. So here's what I'd like us to do. I'd like you to start off with an exploration or a thought exercise. Notice what the problem says. It says you sold a total of $16 worth of tickets to a fundraiser. You lost track of how many of each ticket you sold. If adult tickets cost $4 each and children or child tickets cost $2 each, let's see if we can come up with a list of possible combinations of what we could have sold. Now, I'd recommend at this point that you pause the video, take out a sheet of paper, and try this on your own. It's going to be much more helpful for you to do that than to just listen to me rattle off several answers. Because this is a video, I am not going to sit here and wait on you to do that. I'm going to go ahead and rattle off some answers or some examples, hoping that you have done that on your own and what I'm about to do does make sense. You can do this with a series of trial and error and some guess and check. Here's what I happen to notice. If adult tickets cost $4 each and I sold a total of $16 worth of tickets, if I count by fours, $4, $8, $12, $16, it is possible that I could have bought 4 adult tickets and not purchased any children's tickets. I buy 4 adults at $4 each, that's $16, plus $0 in children's tickets is a total of $16 worth of tickets. Now, it is possible that if I did not buy all adult tickets, maybe I only bought 3 adult tickets, that I might have needed to purchase some children's tickets. Or I should say I might have sold some children's tickets to make up the difference. Because 3 adult tickets at $4 each is only $12. That means I have $4 left for children's tickets. If they are $2 each, I would need to buy 2 of them. 3 $4 tickets is $12, 2 $2 tickets is $4 for a total of $16. And because I'm trying to keep this organized, I'm just going to go ahead and count down 4 adult, 3 adult, 2 adults, and then I'm going to fill in the leftovers with children's tickets. 2 adult tickets is $8. That leaves me $8 left for children's tickets, which means I can buy 4. And I'm going to go ahead and fill in the rest of my table for you. Now, here's what I'm going to do. I'm going to take each of these pairs of values. Remember, pairs of values can be thought of as coordinates. And I'm going to graph them over here on the right in this coordinate plane. Notice that my coordinate plane only has positive values along the x-axis or horizontal axis because I couldn't sell negative tickets. Same thing for my y-axis. Notice I only go up from 0 because I can sell numbers of children's tickets, but I can't sell negative children's tickets. And then I'm going to graph these points on this coordinate plane. Notice 4 adult tickets and 0 children's tickets has me going over 4 and up 0, which is here. 3 adult and 2 children's tickets, that's over 3 adult, up 2 children's, and I'm going to follow all the way through. Notice that everything on this line is a possible combination that would add up to $16. Whether it be 4 adult and 0 children or 3 adult and 2 children, none of that really matters. One thing I should point out, though, is because we are talking about physical tickets, fractional answers do not make sense along the way. So I can't sell like 3.5 tickets of one type and half a ticket of another or anything like that. I did go ahead and connect the dots because I wanted you to see that these dots are in a straight line, or this is in fact a linear relationship. Now, in this linear relationship for today, our focus is going to be on the intercepts. In fact, if you look back at the original title slide, the title of this lesson was Linear Equations in Standard Form. And when things are in standard form, which we're going to talk about in a second, we pay a great deal of attention to this point right here, where you cross the x-axis, and we pay a great deal of attention to this point here, where we cross the y-axis. If you think about this point right here, where you cross the x-axis, that's referred to as the x-intercept. Intercept just means where you encounter or cross paths with. If we think about this x-intercept in terms of the tickets, what does the point 40 mean in terms of the number of tickets we bought? Hopefully you've had a chance to pause the video and think about that, and hopefully you've realized that the x-intercept represents the maximum number of adult tickets that we could have sold. In other words, if I sell 0 children's tickets, if all the tickets I sell are adults, this is the number I would come up with. I can't sell 5 because that would be more than $16, and I can't do 6, 7, 8, and so on and so forth. Now that you've seen that example, think about what's happening up here at the y-intercept, where we cross the y-axis. This is the point 0, 8. Can you think about what that means in terms of tickets? Hopefully you've paused the video and done that. I'm going to go ahead and tell you that the y-intercept represents the maximum number of child tickets we could have sold. If we sold 8 children's tickets, that's $16, meaning there's no money left for adult tickets. This point, the y-intercept, this point, the x-intercept, we're going to spend a lot of time talking about today, so make sure you're comfortable with that. By the way, we can also represent this verbally by saying, if I wanted to write an equation, it's going to be $4 times the number of adult tickets sold, combined with $2 for every child ticket sold, for a total of $16. Or if I wanted to write that algebraically, 4 times adults plus $2 for every child, or 2 times the child's tickets, is or equals $16. For A being the $4 per adult ticket, if I sell 1 adult ticket, it's $4, 2 adult tickets is $8, and so on. Combined with $2 for every child's ticket. If I sell 1 child ticket, that's $2, 2 children's tickets, that's $4, and so on. And when I combine those, I get a total of 16. This algebraic model is a representation of this story in standard form. We're going to talk a lot about that here in just a couple minutes, so just make sure you're paying close attention to the pattern that you might see. Before we move on, I do want to point out that there are lots of integer combinations that occur just down here below the line that I've graphed. It's actually between the line that I've graphed and the x-axis and the y-axis. I've put yellow dots here for all the integer values. Do you have any idea what those dots represent? Hopefully you've had a chance to think about that. Each of these dots represents a combination of adult and children tickets, or adult and child tickets, that can be purchased for less than $16. Remember, our line here represents everything that would cost exactly $16. Everything that's underneath our line, or I should say that's trapped in this section behind our line and the y-axis and the x-axis, all of these are possible combinations of tickets that you could you could have sold if you have less than $16. So for example, I might have sold 2 adults and 1 child. Well, that's $8. This would be $9. Everything that's over here on the right, these are numbers of tickets that I could not have possibly sold unless I had more than $16. Does that make sense? Tell you what, let's try another one. Here's a sample problem very similar to that. I'm going to recommend that you pause the video for just a second and try some of this on your own. If you get stuck, go ahead and restart the video. We'll walk through at least portions of it together, but try and do as much of this on your own as you possibly can. The story says, you sold a total of $40 worth of cheese. You forgot how many pounds of each type you sold. Swiss cheese cost $5 per pound. Cheddar cheese cost $4 per pound. Can we create a verbal model that shows the relationship between the cost of the Swiss cheese, the cost of the cheddar cheese, and the total amount of money? Can you do that? Let me talk you through it. We know that it's $5 for every pound of Swiss, combined with $4 for every pound of cheddar, for a total of $40. Algebraically, we would say it's $5 for every pound of Swiss. So if I sell 1 pound of Swiss, it costs $5. 2 pounds of Swiss costs 5 times 2 or $10. 3 pounds of Swiss is 5 times 3 or $15. However much I spend on Swiss, that is going to get combined with how much I spend on cheddar. It's $4 for every pound of cheddar. Notice I'm using C for cheddar. So if I buy 1 pound of cheddar, it's 4 times 1 or $4. 2 pounds of cheddar is 4 times 2 or $8. 3 pounds of cheddar is 4 times 3 or $12. And when I've bought both of these, I know I will have spent a total of $40. This is an algebraic model of this story. This actually is going to be a linear equation. It is also in standard form. If you're not sure what standard form looks like yet, compare this algebraic model to the algebraic model you wrote on the previous slide. We're going to approach this one slightly differently. You'll remember last time I made a table of different combinations, and then I plotted those dots on the line in order to discover that this was linear. I'm not going to do that this time. Instead, what I want to do is I want to begin by realizing if we have an equation that is in standard form of a linear equation like this, then we know it's going to give us a straight line. We're going to have a line that goes through somewhere on this graph. The second thing that I know is that I can, instead of making a table of all the possible combinations and plotting all the dots, I can just find a couple dots and they will indicate for me where the rest are. Because if I already know this is going to be a straight line, then I know any 2 dots that are connected are going to form that line. So instead of just guessing and checking randomly, I'm going to pick 2 specific points. I'm going to find the x-intercept and I'm going to find the y-intercept. And once I know those, I can just connect those to give me all the other possible combinations. Remember, the x-intercept is where I cross the x-axis, which means it might be the point 10, or it might be the point 20, or it might be the point, we don't know. But what we do know is that when we cross this x-axis, the y value is going to be a 0. Either it's 20 or 30 or 40 or 5, we don't know, but we do know the y value is a 0. So when I'm finding the x-intercept, I'm going to take this original equation, and I'm just going to stick in a 0 in for y. Or in this case, because the y-axis is cheddar cheese, I'm going to stick a 0 in for c. And then I'm just going to use some computation, some algebra skills to figure out what value s would need to be. Remember, 4 times 0 is just 0, and adding 0 doesn't do anything. To get rid of a times 5, I'm going to divide both sides by 5, and I come up with s is an 8. So my x-intercept says if I buy 8 pounds of Swiss, then I can afford 0 pounds of cheddar. Do you think you can figure out how to find the y-intercept without me explaining it? You might want to pause the video and give that a shot. Otherwise, I'm going to keep right on going. The y-intercept is where you cross the y-axis. In other words, if I buy 0 pounds of Swiss, how many pounds of cheddar could I afford? Notice the coordinates here. This is 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. What I know is regardless of where I cross this y-axis, the x value is going to end up being a 0. Notice I did go back and put my dot in at the 8, 0. Sorry, I meant to do that transition before I talked about the y-intercept, but we'll just keep going. Anyway, for the y-intercept, 5 times 0 is 0. That 0 plus anything stays the same. To get rid of a times 4, I divide both sides by 4, and I get c is 10. So I get the coordinate 0, 10. 0, 10. In other words, if I buy 0 pounds of Swiss, I can afford 10 pounds of cheddar. And I'm going to go ahead and put that dot in for you this time. Notice I have a dot here. I have a dot here. All my other dots are going to fall along that line. We know that because this is a linear equation in standard form. Now, if the x represents the x-intercept represents the number of pounds of Swiss I can buy when I buy 0 pounds of cheddar. That makes this, the x-intercept, the maximum amount of Swiss I can buy. This dot up here says, if I buy 0 pounds of Swiss, how much cheddar can I buy? So this is the maximum amount of cheddar that I can buy. If I wanted to write that as a domain, remember the domain says, where does our graph go from left to right? Well, my domain says I can buy anywhere from 0 pounds of Swiss all the way up to 8 pounds of Swiss. Or the amount of Swiss cheese that I can buy can be any value as long as that amount of Swiss cheese is between 0 and 8 pounds. Does that make sense? Notice I'm using the function notation that we learned back in our functions unit. This tells me what I'm talking about. It says all of these will work. This says as long as, and here's the condition it has to meet. Maybe you can try the range on your own. Remember, range is where our graph goes up and down. Think you can fill that in? Hopefully you've tried that on your own. I've said that the range is the amount of cheddar. Notice cheddar is on the y-axis. The amount of cheddar can be any amount of cheddar as long as it's between 0 and 10 pounds. 10 pounds is the maximum amount I can buy. 0 pounds is the minimum amount that I can buy because I can't buy negative or sell negative amounts of cheese. What do you think about that? Is that okay? Remember, this line right here gives me every combination of Swiss and cheddar that costs exactly $40. Now notice there are some fraction and decimal values here. It looks like there's a fractions about 6.5 and slightly less than 2. Because cheese can be sold in half pounds and quarter pounds and in ounces, every value along this line works, not just the integer values. Not just the integer values. Keep in mind that this section right here underneath my line, between my line and the two axes, that piece right there is every amount of Swiss and cheddar that you can buy that costs less than $40. And this section up here at the top represents every combination of Swiss and cheddar that you can buy that costs more than $40. My line divides my graph into two half planes. The side over here being less than $40, the side over here being more than $40. Hopefully this is starting to come together for you. Let me formalize this just a little bit. When we talk about the standard form of a linear equation, it's when an equation is written in the form ax plus by equals c. Ax plus by equals c. Or using this example right here, 3x plus 4y equals 12. Now, if I wanted to graph something that was written in standard form, most of the time, the easiest way to graph it is the way we just did on the previous example, and that is to look for the x-intercept, or where it crosses the x-axis, and to look for the y-intercept, where it crosses the y-axis. The reason for that is when I go to find the x-intercept, I'm going to be plugging a 0 in for my y, which is going to make this much easier to calculate than it would be if I were just randomly guessing x's and y's. So for my x-intercept, I start with something comma 0 because I'm going to go over a certain number and up 0. I rewrite my original equation in standard form. I plug in the 0 that I know has to be there for y. 4 times 0 is 0. 3x plus 0 is just 3x. And then I divide away the 3. My x-intercept is the coordinate 4, 0. That's right here, over 4, up 0. When I go to do my y-intercept, I'm going to duplicate that process, except this time, instead of sticking a 0 in for y, I'm going to stick a 0 in for my x, because when I cross my y-axis, it means go over 0, up a certain number of places. Again, I rewrite my original equation. I substitute in the 0 for the x this time. 3 times 0 is 0. 0 plus 4y stays the same. And I divide both sides by 4, and I get y as a 3. My y-intercept is the coordinate 0, 3. or it's this coordinate right here. Now, if I look at the distances between my y-intercept and my x-intercept, you'll notice that I have a slope of down 3 and right 4. Down 3 and right 4. This line is going to go through my x-intercept and my y-intercept, but when I'm drawing this by hand, it's sometimes difficult to get all those dots to line up exactly right. So what I do is I like to look at this slope, down 3, right 4, and I like to duplicate it a couple times just to fill in some of those other points. Keep in mind that this pattern, down 3, right 4, could also be written as down 3, right 4 this way, or up 3, backwards 4, and give me a point here. Down 3, right 4, or up 3, back 4, and give me a dot here. The more dots you put on your graph, the easier it's going to be to make sure that your line is not accidentally crooked. So once you have your x-intercept and your y-intercept, look at that slope and fill in some extra dots for yourself. That's really about it. Everything else that we're going to do is looking at more examples of the same thing. So make sure that you have mastery over what does standard form look like, and then how do I find my intercepts. Keep in mind, to find your x-intercept, you're looking for x because you know y. Keep in mind that when you're looking for the y-intercept, you have your x, you're trying to find the y. Tell you what. Take just a second, pause your video on a sheet of paper, try and find the x and y intercepts for this one, and do the graph. I'm going to go ahead and do this out loud as we're going. For me, when I go to look for my x-intercept, I like to do this mentally. It's not really overly complicated calculations, so probably you can look at this and say, okay, if I'm trying to find the x-intercept, I know this minus y is going to turn into a 0. So if I were doing this in my head, mentally I'm crossing this out, and I'm just solving 2x equals 4. Well, I know to divide both sides by 2, and I'm going to end up with x equals a 2. Your x-intercept is going to be 2, 0. And we'll put that dot here. When I go to do my y-intercept, I'm going to do something very similar to that, in that I'm going to go through here and realize my x is going to be a 0, and 2 times 0 is going to go away, leaving me with just negative y equals 4. I divide both sides mentally by negative 1, and I get y is a negative 4. That's here. Once I have those, again, I'm going to look at my slope. This is up 4, right 2. And I'm just going to continue that pattern a couple times to give myself a straight line. Remember, you can also do up 4 and right 2 from behind it, which is the same as down 4 and backwards 2, and put in another dot. The more dots you put, the better your chances of making sure your line doesn't accidentally go crooked when you're doing these by hand on your homework. You might want to try this next one. Again, pausing the video allows you to check and see if you know what you're doing before just listening to me explain it. That's probably going to be much more valuable to you. I'm going to keep right on going. If I'm looking for my x-intercept, I plug in a 0 for y. I know that 3 times 0 is 0, leaving me with x equals a negative 9. So I graph that. When I go to do my y-intercept, let me erase this. When I go to do my y-intercept, I'm going to do something very, very similar to that. I'm going to stick a 0 in for my x. I happen to know using mental math that this is going to turn into a 0, leaving me with 3y equals negative 9. And so I'm just going to divide away the 3. That's 0, negative 3. And there's your graph. Again, I like to give myself extra points, so I see that I'm going to go forward 9, down 3. I'm going to repeat that down here. That takes me to the end of my space. And there's my graph. One more. Again, pause the video. Try it on your own. Your x-intercept is something, 0. That means 2 times 0 goes away, leaving you with x equals 6. And then for your y-intercept, you're going to do something very similar to that. You're going to walk through and say, oh, well, if my x is a 0, 2 times y equals 6 means my y must be a 3. Notice this is down 3, right 6. I'm going to repeat that, and then I'm going to do it backwards as well. giving myself lots of points on which to draw my line. Not too bad, right? We like graphing by intercepts because when we graph by intercepts, most of the time we can do it with some pretty simple mental math because of the zeros that are involved. It shouldn't be overly complex to do that. If you forget, you can certainly do it by hand the long way. The key is x-intercept, 0 goes in for the y-intercept, 0 goes in for the x. A couple quick things I want to make sure I point out. Are there any linear equations that do not have a y-intercept? You might want to pause the video and think about that for just a second. You might want to try by drawing it. Here's a line that does not have a y-intercept. Notice it is a vertical line. We actually use the equation x equals 6 for this line. X equals 6 for this line. The reason for this is that if you look at all the coordinates on this line, this is the point 6, 0, 6, 1, 6, 2, 6, 3. This says regardless of what your y is, x will always be a 6. And notice since it's vertical, it will never cross the y-axis. Are there any equations that do not have an x-intercept? Again, pausing the video, trying this on your own. I'm going to go ahead and let you know that yes, there is one. Maybe it looks like this. It's a horizontal line. It's parallel to the x-axis, therefore it will never cross. Notice as well that if I look right here, this is the point 0, negative 8. This is the point 1, negative 8, 2, negative 8, 3, negative 8. So regardless of what your x is, your y will always be negative 8. Now I don't want to dwell too much on this at this point, but notice that x equals a number is always the equation for a vertical line. Y equals a number is always the equation for a horizontal line. We will come back and talk about that at great length in a future video. Here's just a couple extra examples of word problems where you might see this, just to give you a little bit of extra practice. Again, I'm going to recommend pausing the video between each one of these and trying them on your own, but I'm going to go ahead and fly through them knowing that you're doing this by yourself before you watch the video. You're planning an awards banquet for your school, period. You need to rent tables that seat 180 people. Oh, wait, that's my total. The tables come in two sizes. Small tables seat 6 people. That looks important. Large tables seat 10 people. That also looks important. Give an equation to model this situation, then find the intercepts. Well, let's see. I know that I'm going to have my people per small table times the number of small tables, giving me the total seating at my small tables. For example, it says 6 people can sit at every small table. So if there's 6 people times 1 table, I'm seating 6 people. 6 people times 2 tables is 12 people. 6 times 3 is 18, and so on. I'm going to combine my small tables with my people per large table and my large tables. Again, this is the total number of people sitting at the large tables. It's 10 apiece times however many tables I have. And I can seat a total number of 180. Let's fill that in. I know it's 6 people per small table times the number of small tables. I don't know why this did not pop up. Let's use an S there. I also know it's 10 people per large table. Wow, that didn't show up either. 10 people per large table times the number of large tables, that's 10L, equals my total. And of course, now I can fill it back in. Erase my ink so you can see it just a little bit better. There you go. 6 times S plus 10 times L will equal 180, or if you want to write that more neatly, 6S plus 10L equals 180. Notice it does ask me to find the intercept, so I'm going to do that very quickly. If S is a 0, that would make this go away, leaving me with just this. So 10 times what is 180? 0, 18 is your y-intercept. And if y is a 0, what would your x have to be? Well, 10 times 0 would be 0. 6 times what is 180? That would be a 30. So if I use 0 small tables, I would need 18 large tables. If I use 0 large tables, I would need 30 small tables. Get the idea? Take a look at this one. What if you decide to rent tables from a different company? The new company's rates can be modeled by the equation 4x plus 6y equals 180. Notice this time we're talking about the company's rates, not the number of people that sit at the tables. It says x is the number of small tables, y is the number of large tables. What do we know about the costs? What do we know about the costs? A couple things I want to point out here. This seems to indicate a cost times the number of small tables. This seems to indicate a cost times the number of large tables, which would make this a total cost. If I think about it that way, when I see 4x, it looks like the small tables or one type of table cost $4 and the other cost $6. Remember, this number right here is being multiplied by the number of small tables. So whatever this is counting, it happens for each small table, or the 6 is for each large table. One more problem. You're going on a ride at you're going to the fair and have $45 to spend on rides and games. Ride tickets are $4. Game tickets are $2. Create an equation that models this situation using x for the number of ride tickets and y for the number of game tickets. I think you can do that on your own. It may help to do the verbal model. You have the cost of a ride times the number of rides, and you have the cost of a game times the number of games. Altogether, that should give you your total cost. Can you give me that equation? How about $4 per ride? How about $2 per game, and a total cost? I've got 4r plus 2t equals 180. That's really all we have for today, or I should say all you guys have for today. I need to go back and rearrange or reorder some of these animations on my slideshow, but that doesn't really have a whole lot to do with what you need to accomplish. Thank you so much for taking the time today to watch this. Hopefully it's made perfect sense for you. In our next video, we're going to talk about a different form of a linear equation that's also very useful, the slope-intercept form of a linear equation. So make sure you come back and check us out for that. As always, I wish you guys the very, very best. Take care of yourselves. Bye-bye.